Okay, so talking about mole here and how we can use mole as a way to describe large amounts of atoms, which is what we'll want to do to kind of compare sort of the theoretical understanding of chemistry in terms of something happening between the atoms of these elements, and maybe something we would want to do in a laboratory where we're going to actually weigh out a sample, right? So we don't want to have to count how many atoms are in there. So we're going to use mole instead to give us a more reasonable number. So a few examples here of how we can use some of this information. So we'll work through them, and that should give you a better idea of, right, the importance of, or at least the usefulness of these in terms of the problems we're going to solve. So the first thing we want to do here is calculate the molar mass of this particular compound, C6H8O6. Now again, molar mass is going to be the much more normal term for this. This could also be formula weight. In fact, now that we know mole, we're almost always going to use molar mass here, but that doesn't mean you won't see it as formula weight, molecular weight sometimes, and mass is basically equivalent to weight here because we're talking about things happening on the surface of the Earth. So weight and mass are the same. So you can kind of switch all those different terms in: molar mass, molar weight, molecular mass, formula weight, formula mass. They all mean the same thing. But in this case, what we want to do is just count up basically the masses of these individual components. So in this molecule, I've got 6 carbon atoms, I've got 8 hydrogen atoms, and I've got 6 oxygen atoms. Now I can figure out how much each one weighs by looking at the periodic table. So I think I had a periodic table here somewhere. We just grab our handy periodic table, right? There's one inside the textbook, inside the cover of the textbook if you need to find one. And we just have to find our elements here. So carbon's over here, 12.01. Oxygen over here, 16.00, and hydrogen over here, 1.01. Now the periodic table that I like to use rounds everything to 2 decimal places. That makes sig figs a little easier, right? If you're looking at a different version, you may see slightly different numbers, right, that just go to a few more decimal places sometimes. So I'm going to take those numbers and I'm going to multiply by how many are present. So I've got 6 carbon atoms, and each carbon atom weighs 12.01, right? Now these would be, if we're just talking about an atom, these would be atomic mass units, right? Or sometimes that's abbreviated just as U, like we talked about back in chapter 2. 8 hydrogen atoms, so I'll take 8 and I'll multiply by the mass of the hydrogen atom. 6 oxygen atoms, I'll take 6, multiply by the mass of an oxygen atom. So 6 times 12 is 72. So that would be 72.06 would be the total mass from those 6 carbon atoms. 8 times 1.01 is 8.08. That would be the total mass from those hydrogen atoms in that molecule. And 6 times 16 would be 96.00. Total mass from the oxygen atoms, right? And if I just add that up, 1, 4 there, 10, 6, so 6 carry the 1, would be 176.14. So that would be the total mass of this compound. Now, how are we describing that mass? If we're just talking about one molecule of C6H8O6, we could say there are 176.14 atomic mass units per molecule. So that's how much one molecule of the compound would weigh in AMUs, or atomic mass units. Now, because of the mole, the maybe more useful way we can describe this information, 176.14 is how many grams would correspond to 1 mole of this material. So the relationship between atomic mass units and grams is the same as the relationship between the number of molecules and moles, which is Avogadro's number, 6.02 times 10 to the 23rd. Now this is a much more useful set of information for us because grams is something we can pretty easily obtain in a laboratory setting by putting something on a balance, right? It's kind of hard to weigh things out in atomic mass units. Okay, a couple calculations here that we want to look at here toward the bottom of the page. Now for the next few, and there's one that trails onto the next page, and that'll probably be a separate video. The directions are here at the front. Calculate the mass in grams, right, of what's given there. So 4.24 moles of gold, we want to convert that to mass. So we can again use our units here like we talked about back in chapter 1. If I start with units moles of gold, I want to cancel moles of gold on the bottom. Now, the common abbreviation for moles is just MOL. I will usually write it like that when I'm writing it out. And I substituted the symbol here for gold as well. So AU is the chemical symbol for gold. I need to relate that to grams on top here, grams of gold. Well, that information is in my periodic table, right? Now, this can be a little tricky because you've got to realize sometimes you're going to look to the periodic table for information. Sometimes you're going to find it somewhere else in the problem or unit conversion like kilograms to grams that you memorized. But in terms of mass relationships, those are in the periodic table. So I have to find gold. It's 196.97. So there are 196.97 grams of gold. That is equivalent to 1 mole of gold. Moles would cancel out, and this would give me how many grams of gold are in this particular sample. So again, just like we talked about in chapter 1, the math is laid out there. 4.24 times 196.97. And that is 835.1528. Now, based on the data we started with here, this is 3 significant figures is our limit, so I'm just going to keep 835. So 835 grams of gold. Now, in the molar mass, this is really a measured number, and this is an exact number, kind of like density. It's per mole, the same way density is per volume unit or per milliliter. This really shouldn't be what limits our sig figs though, because most of these we're going to know at least 4 significant figures, right? Unless it's a really small molecule like H2, we might only have 3 significant figures there. Okay, now the second one here, I think we can fit on this video, 0.0063 moles of water. We want to approach this the same way. We want to put moles here because again we're trying to cancel out the units. And I'm going to put in the chemical formula for water here because that's important. What goes up here will be grams of water, right? But that's a molar mass or a formula weight. So this, we can get the pieces from the periodic table, but we can't get this directly from the periodic table. What we need to factor in is the fact that there are 2 hydrogens and 1 oxygen in the water molecule. So if we go to the periodic table and we find hydrogen, it's 1.01, right? And if there's 1 oxygen, that is 16.00. Now that's not too demanding there. 2 times 1.01 is 2.02, plus 16 is 18.02, right? Often the numbers are going to require us going to the calculator to add them together. But 18.02, that would be the molar mass or formula weight of water. So there are 18.02 grams of water in every mole of water. That again cancels out moles. This would give us mass in grams of water as our answer. So 0.0063 times 18.02. Right? And we started with a 2 significant figure number, so I'm just going to keep 2 significant figures here. 0.11 grams of water would correspond to this many moles of water. Okay, we'll stop right there. We'll pick up on the next page in the next video.